Today we have Poobhalan Pillay, and Audrey actually invited him as you know him. But yes, thank you very much, Prof. Pillay, for being here, and we really look forward to your talk. So you can start.
Okay, thank you very much for the introduction, Rocco. Yeah, I appreciate the invitation from the University of Stellenbosch to speak on a subject of my own choosing. And originally, I said I'll speak on limits because you said it's targeted to university students. But then I thought that is such a dull topic. It's a very important topic, but it didn't have the kind of punchline that I would have liked to make in a talk such as this, where we have a rather wide audience. So let's go ahead. So the topic has now changed from unpacking the limit to perfect numbers. All right. So this is my heading. I just want to give a little sales talk here. At the bottom of this first page, you will see a reference. I've written up this entire talk as part of a lesson in a book that I wrote. It's called 1000 Mathematics Olympiad Problems. And that lesson is entitled, what is it entitled? Something like Challenging Problems or Famous Problems or something like that. And one of them is the unpacking of the whole mystery of perfect numbers. Perfect numbers go back a very long way. And somebody, I'm not sure exactly who asked the question or even thought about the concept, but it is a number which is equal to the sum of its proper factors. Alternatively, it is a number that is equal to twice the sum of all its factors. So if you take, let's just illustrate this. If you take example 4, take the number 4. Its proper factors are 1 and 2. And when you add them, you get 3. And that sum of the factors is not equal to 4. So 4 is not a perfect number. If you want to take the alternative definition, 1 plus 2 plus 4, if you include all the factors, including the number itself, now you get 7, and that also is not twice 4. So you can use, if you use all the factors, then the sum of the factors must be equal to twice the original number for it to be a perfect square. If you take 6 now, for instance, when you sum all the factors, you get 12, and that is certainly twice the original number, which is 6. And therefore, your conclusion is that 6 is a perfect number. You try 8, it doesn't work. You try 9, it doesn't work. And then we just jump a little bit up to 28. And if you look at 28, and you look at the factors of 28, you have 1, and you have 2, you have 4. The next one is 7. And the next one is 14. And the last one is the number itself, which is 28. And if you add up all these factors, you get 56, which is twice 28. So 28 is a perfect number. So as far as these small numbers are concerned, 6 and 28 are perfect numbers. So the question that we'd like to ask is, are there any other perfect numbers? What is the next one? The next perfect number is, it jumps quite a bit, 496. So you're going to skip a lot of numbers before you get to the next perfect number. And then
Sorry, Prof, to disturb you. Hello?
Yes.
Sorry,
Rocco?
Dr. Pillay, to disturb you.
Yes.
Sorry to take you back. I want to check something here. Scroll back to that slide. That slide, the one that I've got example, the one that I've got example.
Yes.
You said that 4 is not the perfect number.
Yes.
And what I want to double check here is that a perfect number and a perfect square doesn't have any correlation in terms of looking
No.
at 4.
No, there is no immediate correlation. A perfect number has got nothing to do with the perfect square. Okay, if that answers your question. Can I just appeal? You know, we've got 1 hour and my talk will just barely finish, maybe 50 or 55 minutes. So at the end, towards the end, I can entertain some questions. So if you've got any questions like this one, please just jot it down and you can ask me at the end of the class. Is that okay with you?
Noted, yes.
Yeah,
Thanks.
otherwise I wouldn't be able to finish this talk. Okay, so the next number is 496. The number after 496 is another huge number. It's 8,128. And the question arises, is there any pattern in which these perfect numbers form? So if we just list down the 4 numbers that we've got so far, 6, 28, 496, the one that you're looking at. But what you can see is that they are very sparsely populated. We know that these are the first 4 perfect numbers, and they seem to be increasing quite rapidly. All right, so if the question is there a pattern? And remarkably, there is a pattern. Although it's not immediate to see, the pattern only becomes visible when you try to factorize these numbers. So if you look at 6, when you factorize 6, you get 2 times 3. And we'll write that, okay, we'll come back to that one. 28 is 4 times 7, 4 is 2 squared. 496, when you factorize it, you get 16 times 31, which is 2 to the power of 4 times 31. And then when you come to 8,126, which looks like a terribly huge number, you've got, this is 64, which is 2 to the 6 times 127. All right, so certainly you got powers of 2, but these other numbers here, 3, 7, 31, and 127, a little bit of thought will see that you are 1 removed from a power of 2, you see? This is 4 minus 1, this is 8 minus 1, 32 minus 1, 128 minus 1. So that's where the pattern comes. So I rewrite that as the correct power of 2, the 2 squared minus 1, and 128 goes up to 2 to the 7th minus 1. So when you write these perfect numbers as factorizations, you get a rather nice kind of a pattern here. Right? There are 2 factors. The first factor is a power of 2, and the second factor, if you like to describe it, it's you double this first factor to get 2 cubed and subtract 1. See, like here you got double 16, which is 32, subtract 1. So that is how you get 2 to the power of 5 minus 1 and so on. So that is the general kind of a rule. Now if we continue in the slide, we look at the exponents of 2 that appear in the pattern. They are consecutive integers. And so this is the general form of a perfect number. But one just has to be careful here, because this looks like a general form. You've got a power of 2, and this is the double minus 1. So we have, apart from the powers of 2, the other factors are 3, 7, 31, and 127. Now, interestingly, these numbers here are all prime numbers. So this is a interesting observation, but we're not sure whether this is a pattern. But these are prime numbers, but there are missing numbers. The missing numbers are, if you we saw earlier on that this is, you see, you got 2 squared, but you don't have 2 cubed, and you don't have 2 to the power of 5. So 2 to the 2 cubed is missing, and 2 to the power of 5 is missing. 2 cubed will give you 16 minus 1, which is 15, while the other missing number is 63. Now these 2 are composite numbers. So it now, there's a conjecture that we can make that the perfect numbers are of this type, which we said, 2 to the n times 2 to the n plus 1 minus 1. But this number here must be a prime number. And if this is a prime number, then this number becomes perfect. Now, we don't know that. All we know is that the first four numbers, they look like that. And this is a guess that we are going to take. Because the power of 2 times a prime number gives you the first four perfect numbers. So let's just put that conjecture down. If 2 to the n plus 1 minus 1 is a prime number, then this thing here is a perfect number. We don't know that. We'll have to prove it. We know it's true only for the first four perfect numbers. But how do we know that it's true in general? How do we know that if this quantity here is a prime number, if you multiply by this power of 2, you're going to get a number which has the property that the sum of all its factors is twice the number, right? So I have to prove that the sum of all the factors of this is twice the number, bearing that in mind that this is a prime number. So instead of carrying this prime number as this big load, give it a name, call it P, right? Then you have this quantity 2 to the power of n times P, where P is a prime number, and we want to prove that such a number is perfect, where P is actually equal to 2 to the n plus 1 minus 1. All right, but before that now, we need to add up all the factors of 2 to the n times P. So let's just have a look at this thing. Before we go on, there are two important statements I want to make. To prove this, we need to know two things. One of them, the first one, is that 1 plus r squared all the way to r to the power of n. This is the famous geometric series, right? With first term 1 and common ratio r. And when you add up all these, this is a formula for the sum of n plus 1 terms of a geometric series. So you've got that. All right, but the second one is I'm going to try to find out what are the factors of this, because we need to add up all the factors to prove that this number is perfect. So what are the factors? Now you've only got two prime factors here. You got P and you got 2 to the power of n. So what are the factors of this? The factors of 2 to the power of n, firstly, are all the powers of 2, as you can see here. And then to find the remaining factors, we have to use P, and the only way you can use P is to multiply each one of them by P to get the remaining factors. So there you have it. You've got all these factors and all these factors, and there are no other factors for any number of this form. The reason is P is a prime number, you see. P itself doesn't have any factors. So the only factors for P are 1 and P. That is why I just have two groups here. All right, so these give you the full factors. So knowing that, I can now prove this statement that I was claiming. If 2 to the n plus 1 minus 1 is a prime number, then this number is a perfect number. This is what we claimed. So you got this quantity is a prime number, and it's a perfect number. Okay, so let's take this number that is under investigation. And I'm going to rename, as I said, I'm going to rename this as P, right? And P is equal to this quantity, and that's a prime number, right? That's what's given. We now need to show it's perfect, so we're going to add up all the factors. And we wrote down all the factors earlier on, right? This was the first group of factors. This was the second group of factors. Now we're going to add them because we want to work out the sum of all the factors of n, right? We add them and we try to simplify it, and you see here a little bit of algebra. P comes out as a common factor here in the latter part of this tail, and then once you take it out as a common factor, then you see even this 1 plus 2 up to 2 to the power of n occurs twice. So you can take that out as a common factor. It goes into this one time, and it goes into this P times. And this one here, you have a formula for this. This is the formula that I spoke about, the sum of the first n terms of a geometric series, right? It's going to be r to the n plus 1, which is 2 to the n plus 1. There it is here, minus 1. Okay, there it is here. but over 2 minus 1, because r is 2. 2 minus 1 is 1. So I skipped that thing dividing by 1. So you simply have that this sum, the sum of the first n plus 1 powers of 2 is equal to that. Okay, and 1 plus p, remember, I had that p is equal to this. I'm pointing to this here on the top. Can you see it? And if you look at 1 plus p, 1 plus p, if you bring it to the other side, bring 1 to the other side, that's equal to 2 to the n plus 1. So I'm replacing 1 plus p by 2 to the n plus 1. And now I got a product, but I'm going to take the 2 out from 2 to the n plus 1, and you'll get 2 times 2 to the n times this quantity. And there you have it. This thing here is exactly the same as the original number that we started off with, capital N. See? So this part here is n, so you have 2n. So therefore, the sum of all the factors of n is twice the original number. By definition, capital N is perfect. Okay. Are there anything that you want to make any comments at this stage? I'll allow you to say whatever you want to say. Okay, let me just see how many people are here. All right. So far, what we've got here at this moment is we've got a number of perfect numbers. In fact, we've got quite a lot now, because as long as 2 to the n plus 1 minus 1 is a prime number, then you have a perfect number. All you have to do is to take that prime number and multiply it by 2 to the power of n, 1 less than the power of 2 here, and that becomes perfect. So we have a lot of perfect numbers, depending on whether these numbers of this form are prime numbers or not. So now these numbers here are now under investigation. That if you take a power of 2 and you subtract 1, when is that a prime number, right? Now, these numbers here have been under so much of investigation that they have been given a name. Any number which is of the form a power of 2 less 1, like what we've had so far, 3 and 7 and 31 and 127, any number like that, even 15, and the ones that we're missing were 63, those are all powers of 2 less 1. They are called Mersenne numbers, right? We call them Mersenne numbers. There's the word here, Mersenne. He was, I think, a French mathematician who made a lot of investigations into such numbers. So if you were to construct a perfect number, all you have to do is to take this thing and see whether it is a prime number. And once you got that is a prime number, you've got a perfect number, because all you have to do is to multiply this prime by 2 to the power of n. So now let's have a look at this thing here, 2 to the n minus 1. Don't worry about n plus 1. We just say a power of 2 minus 1. That's the general form. Now, the first question we'd like to ask is, okay, it's a prime number, but for how many values of n is it a prime number? So that's the first kind of a question. So that becomes a conjecture. Right? So the conjecture is, how many such n's are there? The answer is not known. We don't know whether, in the first place, whether there are infinitely many prime numbers of this type. It's an unsolved problem. It's a very famous unsolved problem. And if you have that this is a prime number, then such a number is called a Mersenne prime. So a Mersenne prime is a number which is this minus 1 if it's a prime number. There is another type of a number which is under investigation also, and that is the same thing, 2 to the n plus 1. That question is also a very popular question. Is that a prime number? Those numbers have got Fermat numbers. So I'm not really interested in those numbers in the stock. We are only interested in Mersenne primes because they feature very strongly in perfect numbers. Okay, now here's a fact. If you take n to be equal to all these numbers, we'll say something more about them just now, then 2 to the power of n minus 1 is not a prime number. See? If you look at all these numbers, 4, 5, 6, 8, 9, 10, 12, now look carefully and you will see what are these numbers. Now from the beginning, the 2 and 3 are missing. What's the next one which is missing? The next one which is missing is 7. So 7 is missing here. 11 is missing. 13 is missing. 17, 19. So you see the numbers which are missing here are all prime numbers. So we know that this, if you try these numbers here, you will see that none of these numbers is a prime number. Okay. So here's a claim. Whenever this number is composite, whenever n is composite, the index, whenever that is composite, then this whole number here is also composite. So if n is a product of two numbers which are greater than 1, those are the composite numbers, then it turns out that this number here is also composite. So they don't become Mersenne, they don't contribute to Mersenne primes, right? And the numbers n don't contribute to Mersenne primes because we want this thing here to be a prime number. Okay, what is the reason for that? If n is composite, how do I know that this thing here is composite? So let's prove it. It's very easy to prove actually. See, if n is composite, what does this mean? It means that n is a product of two numbers where each of them is greater than 1. So I assume that n is composite as we have done here. Now I'm going to take the r, the one of the factors, and take 2 to the r minus 1 and multiply it by this rather monstrous object here. Now, when you multiply these two, a very beautiful thing happens. A lot of these terms cancel, right? And after multiplying this entire thing, there are only two survivors. One is 2 to the power of rs, and the other one is 1. You see? If you multiply 2 to the r by the very last one, you'll get 2 to the rs. And if you multiply -1 times 1 here, you get -1. And all the other terms, they cancel each other. So you get this. But rs was originally said to be n, so you got 2 to the n minus 1. All right, and just to summarize, when you multiply these two numbers, you're going to get that. I'm going to rewrite it out again. I'll put 2 to the n minus 1 on the left-hand side. It's equal to 2 to the r minus 1 times this. That's a very beautiful result. It's a very simple result, but a very, very beautiful result. I'll tell you why, and you'll see how it unfolds in a few moments. What's happening here is that we're not already saying, by the way, r is greater than 1, we said, right? For this to be a proper factorization. So therefore, this part here, 2 to the r will be greater than 2. So this part here is not equal to 1. It's a proper factor, right? If r is greater than 1, then r is 2 or 3 or something, then this thing here becomes it's not equal to 1, so this becomes a proper factor of this. So this is not a prime. If n is composite, then this is also composite. But the more interesting thing is that 2 to the r minus 1 is a factor of 2 to the n minus 1, right? Which is, let me just capture that fact. So what we are saying is that if r is a factor of n, right, then 2 to the r minus 1 is a factor of, I should have said 2 to the n minus 1 here. N is rs. So that's an interesting fact. If r is a factor of n, then that quantity is a factor of 2 to the power of this minus 1. Now, just to illustrate this, Now here's an interesting thing. If I take 2 to the power of 35 minus 1, now that's a monstrous number. If you look at it, okay, it's so large that is about equal to the amount of money that was stolen by ESCOM, 35 billion approximately. So you've got a huge number here, billion, 34 billion something. That's 2 to the 35 minus 1. Now, if you try to factorize this, you're going to find it very difficult to factorize this huge number. But we can say immediately the 31 and 127 are factors of this huge monster. Why? Because 5 is a factor of 35. Therefore, 2 to the 5 minus 1 is a factor of this. Likewise, 7 is a factor of 35. Therefore, 2 to the 7 minus 1 is a factor of that big number. And these are the ones 31 and 127. And you simplify them. So that gives you a very nice way of finding factors for numbers of this type. Okay, now one must be a little bit careful here. You might think that if the index is a prime number, then 2 to the p minus 1 is also a prime number. You might be tempted to say that. A lot of novices in mathematics will say that, because we are saying if n is a composite number, then 2 to the n minus 1 is a composite number. And they would use some kind of skewed logic to say, therefore, if n is not a composite number, then 2 to the n minus 1 is also not a composite number. That's not true. That's the converse of that last statement. Right? And it turns out that the converse is not true. What is the converse? The converse says that if the index is a prime number, right, is this quantity here a prime number? The answer is false. Now here's a good example. If you take the index to be 11, which is the prime number, and you calculate 2 to the 11 minus 1, you'll get 2047. And that actually factorizes. It's 23 times 89. It's not a prime number. So even if the index is a prime number, the 2 to the power of that prime number minus 1 is not necessarily, it is, if it is a prime number, goody, because it means now that you've got a Mersenne prime, but it need not be a prime number. All right. So there is a very useful result that this last one says, that if you want to check to see whether you need to look for Mersenne primes, you need only look for the indices which are prime numbers. You don't use indices which are not prime, because those will not give you prime numbers. The only ones which will possibly give you prime numbers are where the indices are equal to prime numbers. Right? Possibly. It need not be, but possibly, because there's no converse to that result. Okay, now, I see here there are people who spend their whole lifetime searching for very large Mersenne primes. Right? The thing is, looking for a prime number, large prime number, is a very important exercise in the world. And the reason for that is the people who make codes, like banks, you don't want to break into the security system of Fort Knox or huge banks and so on. And to do that, interestingly, they utilize large prime numbers. When I say large prime numbers, I mean numbers which consist of a very large number of digits. Now, people, they go around searching for these very large Mersenne primes, but it's not easy to prove that some huge number is a Mersenne prime. But there has been some good, very nice developments to check to see how 2 to the power of n minus 1 is a prime number without having to go through all the factors. They have some very nice, clever ways. And therefore, a lot of people, when they're looking for large prime numbers, they search for the prime numbers amongst the Mersenne primes. They take 2 to the prime number minus 1, and they find out, is this number a prime number, right? And that is what takes up a lot of computer challenge. Now watch this. The great internet Mersenne prime search, GIMPS, has discovered the largest known prime number, Now, take a deep breath and look at that number. That is 2 to the index 82,589,933. The index is that number which is evidently a prime number, right? It's an 8-digit prime number. When you take 2 to that power minus 1, you got to get a prime number, right? And these people who discovered this Mersenne prime search, it must have been a huge computer undertaking. I think they utilized a number of large computers all over the world and put them all together and came up with this thing in December 2018, rather recently. This number has got over nearly 25 million digits. 1,000 got 3 to 4 digits. A billion has got only 10 digits. This has got nearly 25 billion digits. Now, if you write this number down, I just made a rough calculation, it'll stretch to a point in space that is approximately half the distance to the moon. That's how big this number is. And that huge number is known to be a prime number. In fact, it's the largest known prime number. Okay, we know that there are infinitely many prime numbers. Euclid proved that. But to find, there's no largest. So each time you have a prime number, you know that there is something which is larger than that. But at the moment, they got this number as the largest. Okay, now let's get back to our the perfect numbers. The numbers that we have so far, they are all even. So the first question we give to ask 2 questions. Are there any odd perfect numbers? That's the first question. And the second question, which is a little bit subtle, are there any other even perfect numbers? And what I mean by this is that we have a formula for some of these even numbers, but that need not be true that those are the only even numbers. There may be some other numbers where there's no formula, some sporadic perfect numbers, right? So there are 2 questions we need to ask. In the process of finding all possible perfect numbers, these 2 questions become very relevant because we've got a number of even perfect numbers. Then we ask ourselves, are these all the even perfect numbers? That's the first question. And then, are there any odd perfect numbers? If so, what are they? So if you know the even and the odd perfect numbers, then we have all the perfect numbers. So these 2 questions are very relevant in trying to find out what the perfect numbers are. Okay, so the answer to the first question is, are there any odd perfect numbers? The answer is nobody knows. It's an unsolved problem. And if you solved it, you will achieve instant fame because people have been working on this problem for well over 100 years, maybe 200 years, trying to find odd perfect numbers. In fact, people are still at it. But what they have concluded, so far they've tried a number of odd perfect numbers. Believe it or not, they went up to a number which has got numbers which have got 1,500 digits in it. And they found that amongst those odd numbers, there wasn't a single perfect number. So if there is such a perfect number, an odd perfect number, the first one will have more than 1,500 digits. You know, these subjects are mind-boggling, you know, and it also sort of gives you a taste of what infinity looks like. You see, another thing, I must tell you this, that there is a high probability that there are odd perfect numbers. There's a very high probability that there are odd perfect numbers. You can prove it using probabilistic arguments. So it means that there are some perfect numbers, odd perfect numbers sitting somewhere, but you don't know where they are. Most ordinary people, when they come to a figure with 1,500 digits, they say, damn you, differently, there are no odd perfect numbers. But mathematics are not like that. Right? You have to prove it. You can't make any such assumptions. Okay, so now before we go on, I just want to talk about the even perfect numbers. There's a very interesting observation I want to make here about perfect numbers. And it is this. Let's take the perfect numbers that we have, but I'm going to take the numbers which are greater than 6. Don't take the first one. Take 28, 496, 8128. Now, you can write this very beautifully as a sum. Watch. 28, 1 plus 27. Okay, that's clear. If you add these four numbers, you'll get 496. Now, can you see what these numbers are? 1, 3 cubed, 5 cubed, 7 cubed. These are the cubes of the first four odd numbers. And that gives you the second perfect number. Interesting, curious, beautiful. Now, it doesn't stop there. If you take this one and take the odd numbers again, the cubes of the odd numbers, 27, 125, 343, 729, 9 cubed, 11 cubed, 1,331, 13 cubed is 2,197, and 15 cubed. When you add up all these, shockingly, beautifully, the answer is 8,128, which is the fourth perfect number. So now we have a conjecture. The conjecture is that the sum of cubes of odd numbers, starting from 1, is going to be a perfect number. The only snag is that you don't know how many to take before you get to the next perfect number. But if you count the number of terms here, even there is a pattern. The first one has got 2 terms. The second one has got 4 terms, which is 2 squared. The third one has got 8 terms, which is 2 cubed. So here is the, when you bring it down, you'll see this is there's a pattern here somewhere. That this perfect number, let's take the third one, or the fourth one. 2 to the 6 times 2 to the 7 minus 1, that's your 8,128, is equal to 1 cubed plus 3 cubed and so on, going up to the sum of the first odd numbers up to 8 terms, 2 cubed terms. Now, how do you get the cube? The cube is a half of 6. So it's 2 cubed terms. The next one is 2 squared, the previous one, and that is half of 4. And so the number of terms is going to be half the index of 2 in the representation of this as a product of a power of 2 and a prime number. Okay, but now these indexes, how do you know there's a half? Interestingly, if this number is perfect, then the index is always even. There'll always be a half. Right. So that's another very interesting fact. So yeah, okay. I'm sorry I had to go down. I was busy preparing the lecture, and then suddenly the load shedding hit me at 10 o'clock. So I lost 2 hours. And I cleaned it. I was cleaning it up, but it didn't save it. So here, why is n even in this perfect number? I just made that statement that n is even in this perfect number when n is greater than 1. Okay, for 6 you have 2 to the power of 1. That's not even. For n greater than 1, we are saying this even. There's a very, very beautiful reason for that. You see, if n is odd, then n plus 1 is even. And if you look at this second factor, this thing here, n plus 1 is, say, 2k is even. And this is 2 to the power of 2k minus 1. And we just said that as long as you got a factor of n, then 2 squared minus 1 is a factor of this. See, just as I said earlier on, because 2 is a factor of the top. So you got 2 squared minus 1 is 3. So this 3 is a factor of this number. And this is greater than 3, this thing here, because the n is greater than 1. So therefore, 3 is a proper factor of this. This is not equal to 1. It's actually greater than 3, greater or equal to 3. So you've got this thing here is not a prime then. It's a contradiction, right? So if n is odd, you get a contradiction. Conclusion, n is even. So this index here that we have here is an even number, right? So then I can speak about half that even number. And that is what we do in this. So let n be equal to this. This is my conjecture now. We're deriving this conjecture from that observation that we had here, right? That if you got a number of the form 2 to the power of n into 2 to the power of n plus 1 minus 1, where this is a prime number, then you are going to get it to be a sum of the first cube of all numbers. Sorry. Okay, so let's just prove this result here now. But before we prove this result, I want to share something with you. A very useful fact. The sum of the cubes of the first n natural numbers. You know the formula for 1 plus 2 plus 3 all the way up to n. Right? That's the sum of the first n natural numbers. And it's an arithmetic series. So it's n into n plus 1 over 2. We know that. But there is also a formula for the sum of the cubes of the first n number. There it is. 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. This is the formula. Okay. So I'm not going to go through the preamble on this thing here. The formula is the square of n multiplied by n plus 1 squared, the square of the next one, divided by 4. So there's a beautiful formula for the sum of the cubes of the first n numbers. Like for instance, if you take 1 cubed plus 2 cubed plus 3 cubed, right, you square 3, which is 9, and you square 4, which is 16, multiply them out, 9 times 16, but you divide the answer by 4. So you get 9 times 4, which is 36. All right, so that's a nice, beautiful formula for the sum of the cubes of the first n numbers. And I'm going to post these notes out along with the talk. Well, I'm not going to do it. I trust that the people in Stellenbosch will post this PowerPoint together with the audio, the recording, so that those who have missed this talk will have it available. And those of you who have been in it, you can go over it to understand those things which you didn't understand. Okay, so now we want to prove this. So I'm going to prove that 1 cubed plus 2 cubed going all the way up to 2 to the power of n over 2. If you remember, this is what we got, 2 to the power of n over 2 terms. We want to prove that this number here is equal to n. This capital N is this number that I keep speaking about, 2 to the power of n into 2 to the power of n plus 1 minus 1. So we want to prove that. Okay, and it's not very difficult. There's a little bit of algebra involved in this. As I said, I've just got 14 minutes. I don't have too much of time. But the strategy is like this. We don't know what this is. Call it x. We want to prove that x is equal to 2 to the power of n into 2 to the power of n plus 1 minus 1. We want to prove that. Right, knowing that one of those factors is a prime number. Okay, so let's go. So you have this x. Now the trick is there are teeth missing here. The even numbers are missing, right? This is going up to m terms. We're calling m, the 2 to the power of n over 2, we give it a name, we call it m terms. What we do is we take all the even ones to m terms and perform the same sum. 2 cubed plus 4 cubed plus 6 cubed going up to m terms, and we give it a new name. Remember, we are trying to solve for x, but I now created a new term, y, which is the missing numbers. When you add x and y, you're going to get all the numbers, the evens and the odds, but they are m odds and m evens. So there are two m numbers that you're adding here. X plus y is the sum of the cubes of the first two m numbers. And we said that this is n squared, so you got 2m squared, and then you add 1 to that, 2m plus 1, right? Square that and divide by 4. So this is x plus y, right? I want to find x. So how do you find x? Well, I need to know what y is. And if you look at y, it's 2 cubed plus 4 cubed plus 6 cubed and so on. And there you can take out 2 cubed as a common factor from each one of them. And there you got it. Y is equal to 8. 2 cubed is 8. And then when you take it out, you have 1 cubed plus 2 cubed plus 3 cubed. And that we already know a formula for that, right? It's to m terms, so it will be m squared plus m plus 1 all squared over 4. So now we can find x, right? All you have to do is to take x is that quantity and you remove y from it. So you get this. So we now have a formula for x. When you simplify that, which I'm not going to spend time over, and replace the m by that thing there, 2 to the n over 2, right? Because that is what m was, the number of terms, then you'll get precisely this quantity here, right? And that is the thing that is under investigation. So it's equal to n. So the x value is actually equal to n, which says that the sum of the cubes of the first n odd numbers is that. Okay, so now the last thing that I need to handle here is, see, we posed two questions. The first question was, are there any odd perfect numbers? And I told you we don't know the answer to that question. Then the second question is about the even perfect numbers. And the even perfect numbers, we know some even perfect numbers because all these are even. Because n is at least 2, you see, so all these are even. We said that n will have to be an even number. But the question is, are there any other even perfect numbers? Not that, to formulate that question, we have to think carefully about this. I am going to make the claim that all the even perfect numbers look like this. There are no others. That's a beautiful solution to this problem. That the only perfect numbers are numbers like this. You don't get any other number which has got some other different form. These take care of every possible perfect number. Okay, perfect, even perfect numbers. We're not worried about the odd ones. We don't know much about them. So the even perfect numbers all look like this. And this is the claim. So, but before we prove that, there are some, it's not an easy thing to prove. So I'm just going to make some statements here about remarks concerning sums of factors of a given number. Right? You can take any number, write down the factors and add them up. Are there any properties? Are there any properties that sums of factors have? Yeah, indeed, there are some very nice, well, one particular property, which I'm going to illustrate. And so we say, let us denote the sum of all the factors of n by S of n. We're going to use a terminology. S of n is the sum of the factors of the number n. So let's look at the example 3 immediately. Take S3. S3 is the sum of the factors of 3, and that's 1 plus 3 gives you 4. Right? The same thing with S4. The sum of the factors for S4 are 1 plus 2 plus 4, and that gives you 7. So we can calculate S of n for any n by adding all the factors of n. Okay, and we know that a number is perfect when you add up all its factors, it's twice n. So this is a nice, neat way of describing perfect numbers. You have an equational definition that S of n equals to n. The sum of the factors is equal to twice the original number. And for prime numbers, you have a very beautiful thing because prime numbers have only got 2 factors. So when you work out S of a prime number, it's only 1 plus P. Right? You can immediately know what the answer is because there are only 2 factors to speak of. Okay. All right. So that's the thing. But the other interesting property of this, we can show that S of 12 is equal to 28. That's not a problem. And then when you work on S of 3 multiplied by S of 4, you will get S of 12. Right? So S of 12 is equal to S of 12 is 3 times 4. So S of 3 times 4 is S of 3 times S of 4. But you might say, oh, okay, I got a lovely rule here. But when you try this, you see it doesn't work because 12 is also 2 times 6. And that's not equal to S of 2 times S of 6. So there is a problem here that when you take 12 and you write it as a product of 2 numbers, you must be careful that those 2 numbers don't have any common factors. See, 2 and 6 has got a common factor bigger than 1, right? Therefore, it doesn't work. But with 3 and 4, they got no common factors. So we have a rule, this is a theorem, which we're not proving, but we are making the observation, that S of a product is equal to Sm times Sn is equal to the product of the S's, provided M and N have got no factors in common. Then you can have this nice little rule here. Okay? So, what I'm going to do now is we're going to prove this thing. It's I'd rather just warn you that the proof of this is very subtle, although I've got all the prerequisites in place here. That is why I'm going to show you the screen, and when this thing is recorded, you can look at the screen and go through the processes in case you didn't understand what I'm going to say. I have only 6 minutes, so I'm going to move through this thing quickly. Right, so the question is the following. If n is perfect, right, is n equal to 2 to the power of n times 2 to the power of n plus 1 minus 1? Can we conclude that n has that form? All right. So the first thing you do is divide n by 2 repeatedly until we are left with an odd number. So in other words, what I do is I take n and I take out all the factors of 2 as far as possible until I come to an odd number, m. So you can write any number as a product of a power of 2 multiplied by an odd number. Now remember, n is an even perfect number, so k is at least 1, right? The index here can't be 0, otherwise n is odd, you see, right? N is a perfect number. We don't want k to be 0. So k is at least 1. Okay, and therefore this thing here, they don't have any other common factors because one is even and the other is odd, so obviously you can't have any common factors. And according to what we just said, n is a product of these two, and these two have no common factors. So the S of n, the sum of all the factors of n, which is the sum of this product here, we just said it's equal to S of 2 to the power of k multiplied by S of m. This is the sum of the factors of m, the sum of the factors of 2 to the power of k. The factors of 2 to the power of k, we know, they are 1, 2, 2 squared, they are powers of 2, right? So we can write down all the factors of 2 to the power of k and add them to get S of 2 to the power of k. And this is a geometric series as we saw earlier on. So you have this equation. So S of n is equal to this. All right, so I'm going through this thing pretty rapidly. So this is what we got. S of n equals 2 to the power of k plus 1 minus 1 times S of m. Now, S of n, now remember, n is perfect, right? So the sum of all the factors of n is 2n. N is perfect. We haven't used that fact so far, right? And n is, we took out all the powers of 2 here, the largest power of 2, as it were. So I can substitute 2 times that quantity and I get this. So S of n equals 2 to the k plus 1 times m. So I can replace this S of n in this equation, the last equation that I wrote. I can replace the S of n by that, and you get this beautiful equation here. The power of 2 times m equals 1 less than the power of 2 times S of m. S of m is the sum of all the factors of m. Now you got the same number written in two different ways as a product. And these two numbers here are consecutive numbers. Now, in number theory, there's a lot of common sense. These two are consecutive numbers. And you got a product here, and you got a product here. The conclusion, well, firstly, the conclusion is that m is a factor of this. I'm sorry. 2 to the k plus 1 minus 1. Let's take this one here. Right? It's a factor of the product. It's a factor of the right-hand side. Therefore, it's a factor of this. But this thing here and 2 to the k plus 1 cannot have any common factors. They are consecutive numbers. So if this is a factor of this product, it has to be a factor of m. This number here doesn't contribute anything towards the factor of this. So you got 2 to the k plus 1 minus 1 is a factor of m. And that leads me to saying that I can write m as 2 to the k plus 1 minus 1 times some other factor. It's a factor of it. Right? And once you do that, then we come to the situation here. I'll go to the next page. So I'm just carrying over my equation. The last thing I had was that m is a product of this and this. N is equal to this because we took out the highest power of 2. We also said k is greater than naught. And then we had this little equation here. Okay. Now watch. At this stage, all the things that I wrote down during load shedding disappeared. So I have 1 minute. I'm going to just take not too long. Let me just. Okay, I've got what I've got here is, can you see the screen? Am I sharing the screen with you? The whiteboard?
Yes, Prof. We can see.
Okay. So what I've got here is this thing here, 2 to the power of k plus 1 times q is equal to m plus q. And I also have that when I substitute it, I get this. So we have that this is actually equal to S of m. Okay. If you put these equations together, you will land up with this thing here. You got S of m is equal to m plus q. All those things which I discovered up to this point can be encapsulated in this equation. Now remember, this is equal to the sum of all the factors of m. And I just want to write down some of these equations. You see, if you look at this, oh, I'm sorry. I should have. There's a key equation here, 2 to the k plus 1 minus 1 times S of m equals m plus q. Okay. And the other one is that m is equal to 2 to the power of k plus 1. We said that this thing here is a factor of m. So q is a factor of m. We write that like this. Q is a factor of m. We also know that m is a factor of m, obvious. We also know that 1 is a factor of m. That's also obvious. And yet, when you add up all the factors of m, you're going to get m plus q. Now you already got m plus q plus 1 here. Right? When you add up the factors of m, you're going to m plus q plus 1. The only thing is you don't know whether this 1 here is equal to one of these. Right? It turns out that then you'll have to conclude that q must be equal to 1. That's the only way you can get this. This 1 cannot be any different from these other two. Otherwise, you're going to get the sum of the factors of m to be more than m plus q. You see, when you add up these factors, but it's exactly equal to m plus q. So the conclusion is that q equals 1. Right. Now, if q equals 1, I can take this out. And you have that m is equal to this. Right? Okay. And not only that, you have that S of m is equal to q equals 1. So it's equal to m plus 1. It means that the sum of the factors of m is 1 plus itself. The only way that can happen is if m is prime. A number has got a number of factors, but if 1 and m are already prime, and we are saying that the sum of all the factors is 1 plus m, that means there are no other factors. So m is prime. This little equation here tells you that m is prime. So you got that this thing here is a prime number, right? And remember our original n, we wrote it as 2 to the power of k times m. Now we just can replace this m by 2 to the k plus 1 minus 1. Right? And there you have it. This last thing that I wrote tells me that the even perfect number is of the form power of 2 times 1 less than a power of 2, where this quantity is a prime number. That tells me that any even prime number, even a perfect number, is one of these numbers. And that is where I stopped.